Molecules, now we're talking about the formation of molecules. Molecules are the compounds with two or more atoms. Okay, we've been talking only about atoms so far. Now we're talking about molecules where two or more atoms are joined or combined in some way. Now, when you join two atoms together, they're joined by chemical bonds. And these are the product of how atoms share those valence electrons. In these bonds that occur, you end up storing energy. Okay? And in this case, energy is the capacity to cause change. We'll talk more about this in a bit. This is a really good example of what we talked about. Let's see. Lecture 2.1, an emergent property. So many compounds have different properties than their constituent elements. Let's consider sodium, for example. Sodium by itself is a very soft, silvery white metal. It's atomic number 11, so it only has one electron in its outer shell. So it'll happily give away that one outer electron. I should note, most reactions occur because elements are trying to reach a stable shell. So either basically to attain 8 electrons in their shell. Either if it's 8 in the outer shells or 2 in that first shell, depending on how many shells they have, right? But most of the time they're trying to reach 8 electrons in a shell. So getting back to sodium here, its atomic number is 11, so it has 11 protons, 11 electrons. So you have 2 in the first shell, 8 in the second shell, and 1 in the third shell. So it wants to get rid of that one kind of rogue electron by itself to get down to that stable 8 second shell. That makes sodium very reactive by itself. You can find some pretty cool videos of people taking a piece of sodium and just chucking it in water and it basically like explodes. It's pretty wild. Okay. So that's sodium. Now we have chlorine. Chlorine is on the other side of the spectrum here on the periodic table. It has, its atomic number is 17. So that means it has 7 valence electrons and just needs one more to have a full 8 valence electrons. Well, it sounds kind of like a match made in heaven. Another thing to think about with chlorine, chlorine in its kind of natural form, pure elemental chlorine, is a yellowish gas that is highly, highly toxic and quite notable for applications in chemical warfare, like in World War I when it was used as a weaponized gas. Really brutal, really nasty stuff. But, right, like it said, it wants one electron to fill up its outer shell, and sodium wants to give away one electron so it can get down to an 8 electron shell. So it's kind of a match made in heaven. And sure enough, those two combined form NaCl, or sodium chloride, also known as table salt. Very different than the constituent products. As far as I know, nobody has either exploded or been viciously poisoned by table salt. Okay? So this is definitely an example of emergent properties. So one of the things that drives how bonds develop is electronegativity, where electronegativity is essentially how likely an atom is going to attract another electron. The more electronegative it is, the stronger the attraction. There are several things that can affect how electronegative an element is going to be, having to do with the number of protons, how many shells they have, etc., etc. But we don't even really worry about that so much in Gen Bio. Just know that there are some elements that are much more electronegative than others. And that's going to be determining how likely they are to attract or pull an electron. The most electronegative element you can see here is fluorine, atomic number 9. extremely reactive and extremely toxic in kind of standard conditions. Basically, it just grabs and rips electrons off of anything it can get its grubby little electronegative hands on. But the second most electronegative element is one that's a little more ubiquitous, one you've probably heard of: oxygen. Okay. So oxygen is very electronegative and is very good at taking electrons from different elements and atoms. Something to keep in mind for later. We'll talk about that more. So when two atoms exchange or share an electron, it will create a bond between them. And the type of bond is determined by the difference in electronegativity. So there's two kind of bonds that result from differences in electronegativity. You have covalent bonds, right? So you have covalent bonds and ionic bonds. And think of covalent bonds, are between atoms, and they share a pair of valence electrons. And it's quite strong. You can think of they are sharing covalent valence. So they're sharing these two between their outer valence shells. These are typically very strong, pretty strong bonds. Hydrogen gas, for example, is bound by a covalent bond, as is oxygen gas, O2. How these valence electrons are shared can change the type of covalent bond it is. So if they have the same electronegativity between the two atoms, for example, in hydrogen gas, they're both hydrogen, so they have the same electronegativity. They share the electrons equally. Polar covalent bonds have a different electronegativity, but it's not so different. So they end up sharing the electrons unequally. They're still shared, they're still kind of mingling about together, but they tend to spend more time around the atom that is more electronegative. For example, in water, oxygen's much more electronegative than the hydrogens that are attached to it. So the electrons from the hydrogen tend to spend more time around that oxygen. So that's why it's a polar covalent bond. So you can see here, this from this diagram, because of this kind of unequal sharing, you can have molecules to have sides, where because oxygen is more electronegative, it's more likely to have those electrons around it. You tend to be this side of the oxygen side of the molecule tends to be more negative on average, right? Okay, that'll be important later. But first, let's talk about ionic bonds. So this is when you have elements where one element is significantly more electronegative than the other, and it basically just steals that electron away. So sodium and chlorine are a great example of that, as well as other salts. So sodium chloride, like we just talked about, is a great example of an ionic bond. So you have sodium there, you have chlorine on the complete opposite side of the scale, huge difference. There's going to be a massive amount, there's going to be, chlorine is just going to steal that electron right away. So when it does this, though, when it steals that electron, it's going to affect the charge of each atom in the molecule. Sodium, for example, loses that negatively charged electron, so it becomes positively charged. Chlorine, on the other hand, it gains that the negatively charged electron, so it becomes negatively charged. So they're still, in this formation, but you have one that is kind of more positively charged, one that is more negatively charged because of how they have exchanged these electrons, and so they're now ions. A sodium ion and a chlorine ion. Before we move on here, just a quick note. In a chemistry course, they would typically talk about ionic bonds being much stronger than covalent bonds because there's this strong kind of attraction and pull between the two, since they've very intensely exchanged this electron. In general biology, and in biology typically speaking, we talk about things a little differently, because in biology we're always in an aqueous solution, or a solution with water. We're always around water, right? Every biological system has water involved. So water typically will weaken or change the bond in these ionic bonds. Think about dissolving salt in a jar of water, right? You toss some salt into water, you shake it up, it dissolves. Kind of the same basic principle applies in biology. So typically when you talk about bonds in biology, you usually consider a covalent bond in biology stronger than an ionic bond in biology. And this is a bit of a point of contention between the biological systems versus pure chemistry systems, but it's just something important to note for future reference. Now, in both of these cases, covalent bonds and ionic bonds, those are bonds between specific atoms. The next ones we're going to talk about are a little different. Van der Waals interactions are actually interactions between molecules. So two or more atoms that have already joined together, well, now they're interacting with two or more atoms that have already joined together. For example, water is a phenomenal example of that. And these interactions, let's see if this little formation will work. Yeah, here we go. So these interactions occur because we were talking about this, the polar covalent bonds earlier, and how you can have electrons kind of more likely to be on one side of a molecule or another. This can result in this particular process where you have one portion of one molecule that is at times more likely to be positive or negatively charged, and then you have a portion of another molecule that at times is more likely to be positively or negatively. Let's just make it simple. You have molecule A, you have this side of molecule A is more likely to be positive charged. You have this side of molecule B that is likely to be negative charged. So they're likely to be drawn together like this. Okay? And that's just because of how the electronegativity of the constituent atoms within each molecule are affecting the distribution of electrons. Does that make sense? Hopefully that makes sense. Okay. So what this means is that you have these attractions that can form between molecules that will pull them together. Now, by themselves, these individual van der Waals interactions are not necessarily that strong. But when you have lots of them occurring across a very large molecule or multiple molecules, it can become very strong. So by themselves, not so strong. Lots of them, quite strong. Typically not as strong as a covalent bond or probably even an ionic bond. Certainly a single van der Waals interaction or hydrogen bond is not as strong as either of those. Okay? There's a couple of different types of van der Waals interactions that we kind of talk about. London dispersion forces, which we don't really talk about so much in general biology. And then hydrogen bonds are the big one that we talk a lot about in general biology. And we're going to talk a little bit more about in lecture 2.3 just coming up. But to summarize, you have covalent that are polar and nonpolar. You have ionic, and then those are both covalent and ionic are between atoms. And then you have van der Waals, which includes hydrogen bonds that are between molecules because of how the electrons are distributed. Next lecture, we're going to be discussing the emergent properties of water. including hydrogen bonds, cohesive behavior, how water moderates temperature, how it expands upon freezing, and how it functions as a solvent. Before we get to that content, though, let's quickly go through a lecture question, or at least look at the lecture question. 2.2. Which of the following are true about the single valence electron found in the element unicornium's fifth shell? Note here, unicornium is not actually a real element, but let's pretend it is. So, does this valence electron have more potential energy than the electrons in the first shell? Will it steal electrons to make a complete shell of 8? Does it have a positive charge? And is it in the outermost shell? So you need to identify which of these are true and then select the correct answer from the bottom here. So figure that out before you get to lecture 2.3, again, where we're going to be talking about the emergent properties of water. Thanks. Bye.